Imagine looking up at the night sky and realizing that most of the universe is invisible. For centuries, an enormous amount of time and effort has been devoted to studying the nature of gravity, the most prominent force in the universe, and trying to understand what it is. The topic that we're covering today, dark matter, is a critical component of that puzzle. Even though it has never been directly observed or detected, it is a big part of our standard model of astrophysics. We may not be able to see it, but we know it's there, and it's one of the largest and biggest puzzles in the cosmos. So why has it been so elusive, and how do we search for something we really can't see? Dark matter is an unseen form of mass that influences galaxies' gravitational fields but has not been seen or detected yet. According to this theory, it's some kind of undiscovered elementary particle with properties that don't fit our relatively rigorous standard model of particle physics. One of the most mysterious properties of dark matter that has prevented its detection for decades is its apparently electromagnetic neutrality, or inability to interact with electromagnetic forces. It's like a ghost, unseen and undetectable, but still leaving its mark on the physical world, if you do believe in ghosts. Therefore, it does not absorb, emit, or reflect light. This renders the particles completely invisible. Despite Hubble and James Webb's incredible capabilities, it evades the many eyes of our electromagnetic observatories. Scientists, however, are confident that it does exist, or that something exists at least in its place, since without a substantial source of missing mass, the present-day structure and layout of the universe would be impossible. We have run many simulations seeking to recreate the universe's history from the moment of the Big Bang, but none of them are able to produce the complexity we observe today based solely on the gravity of visible baryonic matter, that is, the gravity of galaxies and their stars. As much as galaxies themselves are enormous, space is incomparably more enormous, and even the gravity of all the universe's galaxies combined does not really explain why the universe looks the way that it does. In order to explain galaxy clusters, almost half of the gravity-inducing mass in the universe that is required doesn't exist. Accordingly, most scientists believe that most of the universe's mass must be in this dark form, aka dark matter. It's still possible to see the gravitational effect of dark matter, but not enough to prove it. However, the gravitational effects that it does produce still exert an influence in space around it, so that we can see it. Scientists really didn't embrace the idea of a universe's contents being more than its visible matter until the 20th century, but scientists have speculated about it for centuries. Astronomers started noticing the motions of the stars in our galaxies in the 1920s and suggested that there might be invisible mass. There were, however, no tangible signs of missing matter until 1933, when a Swiss physicist named Fritz Zwicky plotted the redshifts of galaxies within the Coma cluster, an astronomical cluster of more than 1,000 galaxies, 330 million light years in diameter, in order to map their movements. As he was studying the motion of galaxies in the Coma cluster, he noticed that they were moving faster than they should have been based on the visible matter in the cluster. He proposed that there must be additional invisible matter present, which he called dunkle materie, or dark matter. By applying the virial theorem, he was able to determine that the cluster would need approximately 100 times more mass to hold its galaxies in the formation that he observed. Because the gravity of the stars in those galaxies was nowhere near substantial enough to bind them together, Zwicky concluded that there must be a substantial amount of hidden mass in the Coma cluster, which he then called the missing mass problem. As the decades passed, not much progress was made in understanding this missing mass. However, in the 1970s, a second indirect line of evidence for its existence was discovered. A pair of physicists, Vera Rubin and Kent Ford, plotted the orbits of each star as it orbited the Milky Way and Andromeda galaxies and other several spiral galaxies to map out their spiral arms. They were especially interested in the stars out on the outskirts of those two galaxies, where gravity should be much weaker. Newton's law of gravity tells us that its strength decreases proportionally to distance from the object that's exerting that influence. That's why stars on the outside of a galaxy, like the Milky Way or Andromeda, should orbit slower than those on the inside, near the center. Our solar system shows a similar pattern with its planets around the sun. But Rubin and Ford found that stars on the outside of these two galaxies seem to be orbiting at the same speed as those closer to the center, some even faster. If their cores were the only thing that bound their structure, both galaxies theoretically would have ejected their stars long ago and torn themselves out of existence. There must be another source of mass allowing spiral galaxies like Milky Way and Andromeda and many others to spin at such incredible speeds and remain bound together for billions of years. This was a sign that an indirect sign of the missing invisible mass had just cropped up again. In 1983, Rubin and Ford published an influential paper called The Rotation of Spiral Galaxies. This discussed the missing mass problem with a focus on galactic rotational curves. According to this paper, the invisible missing mass must outweigh the visible mass in the universe by almost a 6-to-1 ratio, a figure that we still use to this day. There's no question that this missing mass makes up more than 85% of the universe's matter, even if it's completely invisible. Because dark matter has a gravitational influence on the visible matter surrounding it, we can infer its existence through indirect effects, which allow certain properties to be constrained. Lambda cold dark matter, or lambda CDM, is a model of cosmology that uses this understanding. This is the most complete, well-regarded, and widely accepted scientific description of the universe as of right now. And as a whole, it ties together the Big Bang, general relativity, and the standard model of particle physics into one comprehensive, complete theory. While it does have its shortcomings, it remains the most comprehensive model that we have for explaining a wide variety of different universe properties. As a core concept of the lambda CDM, dark matter is described as representing about 85% of the universe's mass and just under a third of all of the energy density, aka stuff, in the observable universe. In the lambda CDM model, dark matter particles are generally categorized as either hot or cold. These designations refer to the way that the particles move and interact with each other. Hot dark matter, or HDM particles, are believed to have been moving at high speeds in the early universe. This means that they would have to be moving at relativistic speeds, or close to the speed of light. HDM particles would be produced in the early universe as a result of particle and antiparticle annihilation, and they would have decoupled from other particles early on in the universe's history. This decoupling would have occurred before the formation of large-scale structures like galaxies. The primary problem with the HDM model is that it predicts a different large-scale structure of the universe than what is actually observed. HDM would lead to the formation of smaller structures first, which would then combine to form larger structures. However, observations of the large-scale structure of the universe today show that larger structures formed first and then smaller structures formed later. Cold dark matter, or CDM particles, on the other hand, are believed to have moved relatively slowly in the early universe. This means that they would have low energy and would be moving at non-relativistic speeds, or traveling pretty slow compared to the speed of light. CDM particles are predicted to have formed as a result of the cooling and condensation of baryonic matter, which is basically ordinary matter that makes up the stars, planets, and other visible matter that we see around us in the universe. CDM particles would have been gravitationally attracted to each other, forming the very first structures in the universe. These structures would have grown through mergers and accretion, eventually leading to the formation of galaxies and galaxy clusters. The observed large-scale structure of the universe today is very consistent with the predictions of lambda CDM theory when we assume that dark matter particles are cold in nature. The lambda CDM model has a certain assertion at its core, the Big Bang. The theory of how the universe started out 13.8 billion years ago when a singularity of infinite heat appeared out of nowhere. An unknown reason caused this infinitesimally small point to expand, and since then its extremely high finite temperature has been steadily dropping. The universe began as a hot, dense, and homogeneous soup of particles. Within 20 minutes of the universe's first breath, things began to take place. Subatomic elementary particles began to condense as the universe breathed for the first time. As the universe expanded and cooled, it underwent a period of rapid inflation, during which quantum fluctuations in the energy density of space-time were amplified to form the seeds of structure that eventually grew into galaxies and clusters of galaxies that we see today. During this early period of time, the universe was dominated by radiation, high-energy particles such as quarks, leptons, and gauge bosons. However, as the universe cooled down, these particles became less energetic and eventually gave rise to the very first stable atomic nuclei. This era, known as Big Bang nucleosynthesis, or BBN, occurred within the first 3 minutes after the Big Bang. Although dark matter is thought to have been present in the early universe, it didn't really participate in BBN because most of its interactions only occurred through gravity and the weak nuclear force, which is too weak to influence the formation of atomic nuclei. However, in the early universe, dark matter did help to distribute gas and other matter by providing gravitational potential wells in which matter could accumulate. As dark matter clumped together under its own gravity, it created these potential wells in which gas and other matter could actually condense, and the gas that would accumulate in these potential wells would eventually be heated and compressed by the gravitational forces of dark matter, causing it to become dense enough to ignite nuclear fusion, which powers stars. Without dark matter, gas in the early universe would have been distributed much more evenly, and it is very unlikely that stars would have been formed. Dark matter also played a key role in determining the large-scale structure of the universe. As dark matter clumped together under its own gravity, it created large-scale filaments and voids. Galaxies formed at the intersections of these filaments, leading to the large-scale structure of the universe that we observe today. This process was driven by the gravitational attraction of dark matter, which almost acts as a scaffold that helps to hold the universe together. But what can we deduce about the dark matter's particle properties based on all of these different indirect lines of evidence? Scientists believe it's some sort of novel elementary particle, one that can't be broken down into other substructures like a quark. However, it is a lot bulkier than a quark and even protons. Based on the mass of dark matter and its apparent distribution, it's likely that it's a large, heavy particle with about 10 to 100 times the mass of a proton. While this electromagnetically neutral and invisible particle doesn't seem to interact with light, scientists think that it should interact with ordinary matter in some way. Just a very negligible rate of interaction, far too subtle for us to detect with our current technology. We call this elusive particle the weakly interacting massive particle, or WIMP, because it has such a weak interaction rate. Funny name, right? Our relentless search for dark matter targets these WIMPs. According to our understanding, dark matter forms galaxies in dark matter dense areas, so we should be living right now in a dark matter enhanced area. According to this theory, trillions upon trillions of these invisible particles are expected to be streaming throughout the entire Earth every single second, assuming that they do weakly interact with normal matter. As of now, we've been focused on finding the very rare circumstances when this might happen, but most of the time we're just detecting indirect evidence. However, the search for dark matter continues. Imagine a universe where galaxies are hurtling away from each other, propelled by a mysterious force that we really can't see, feel, or touch. This force, which has been dubbed dark energy, is one of the greatest mysteries of modern cosmology. To understand its discovery, we must first revisit the work of Edwin Hubble, the astronomer who first proved that the universe was expanding. In the 1920s, Hubble used powerful telescopes to measure the distance to distant galaxies and the redshift of their light. Redshift occurs when the light waves are stretched, causing them to appear redder than they would otherwise. This stretching is a sign that the galaxies are moving away from us. Hubble's observations revealed that the further away a galaxy was, the faster it was moving away from us. This relationship, now known as Hubble's law, showed that the universe was actually expanding. Over the next few decades, astronomers measured the redshift of many galaxies and found that their velocities were proportional to their distance, consistent with the expansion of the universe. However, in the 1990s, two teams of astronomers made a stunning discovery. The expansion of the universe wasn't slowing down. In fact, it was accelerating. This discovery was based on observations of Type 1a supernovae, which are standard candles. Their intrinsic brightness is well known, so by measuring their apparent brightness, astronomers can determine their distance. What the two teams found was that Type 1a supernovae in distant galaxies were fainter than expected, indicating that the expansion of the universe was accelerating. These two teams, one led by Saul Perlmutter and the other led by Brian Schmidt and Adam Rees, were awarded the 2011 Nobel Prize in Physics for their groundbreaking discovery of the accelerating universe. But what could cause this acceleration? One possibility was that the matter in the universe was somehow repelling itself, like two magnets with the same pole facing each other. But the amount of matter in the universe wasn't enough to explain the acceleration. Another possibility was that there was some new form of energy that was driving this acceleration. This new energy was called dark energy. So what is dark energy? We don't know for sure, but one possibility is that it's the cosmological constant, a term in Einstein's equations of general relativity that describe a constant energy density throughout space. Another possibility is that the dark energy is a new field that pervades space, similar to the Higgs field that gives particles its mass. Regardless of its nature, dark energy is one of the greatest puzzles of modern cosmology. We know that it exists, but we don't know what it is or why it behaves the way that it does. Understanding dark energy is crucial for understanding the fate of the universe, as its effects will become more pronounced as the universe continues to expand. In fact, current estimates suggest that the dark energy comprises about 68% of the total energy density of the universe. That is more than twice the amount of dark matter, which itself comprises about 27% of the universe. This means that normal matter that we can see and touch, such as stars, planets, and galaxies, make up less than 5% of the total energy density of the universe. Mind-boggling. But perhaps the most stunning aspect of dark energy is its effect on the eventual demise of the universe. If dark energy continues to cause the universe to accelerate, one day it will eventually cause all the galaxies beyond the local group to recede from us at speeds faster than the speed of light. This means that in the distant future, other galaxies will be moving away from us so quickly that their light will never reach us. this will make the universe appear much darker and more empty than it does today. Some scientists have even proposed that this accelerating expansion will eventually tear apart the very fabric of space-time itself, like tearing apart a sheet of paper. To put the scale of this expansion into perspective, consider this. The universe is about 13.8 billion years old. Light travels at a speed of about 300,000 kilometers per second. Very fast. In that time, light could travel about 13.8 billion light years, about the age of the universe, right? Yet, there are regions of the universe that are so far away that light from those regions would take more than 46 billion years to reach us, which is about the radius of the universe. This is because the universe has been expanding since the Big Bang, and the expansion has been accelerating for the past several billion years. So what does this acceleration mean for the fate of the universe? To answer that question, we need to understand the concept of critical density. Critical density is the amount of matter and energy in the universe that is required to just perfectly balance the expansion of the universe. If the universe has more than critical density, its gravity will eventually overcome the expansion, and the universe will collapse in on itself in a big crunch. If the universe has less than critical density, its expansion will eventually overcome gravity, and the universe will expand forever. Current estimates suggest that the universe has a total energy density that is very close to the critical density. However, the amount of dark energy in the universe is increasing over time, while the amount of matter is decreasing. This means that the universe will eventually reach a point where the energy density is dominated by dark energy. At this point, the acceleration of the universe will become so strong that it will overcome gravity, and the universe will expand forever. But how do we know that dark energy is causing this acceleration? One way is to use the cosmic microwave background radiation, CMB, which is the leftover radiation from the Big Bang. The CMB is almost perfectly uniform, with tiny fluctuations that can tell us about the composition of the universe. By analyzing these fluctuations, scientists can determine the amount of dark energy, dark matter, and the normal matter in the universe. Another way to study dark energy is through observations of distant supernovae, like the Type 1 supernovae that we discussed earlier, used by Perlmutter, Schmidt, and Rees. These supernovae are powerful cosmic explosions that can be seen across vast distances. By measuring the distances to these supernovae and their redshift, scientists can determine the acceleration of the universe and the amount of dark energy that is causing it. In addition to these methods, scientists are using other techniques to study dark energy, including gravitational lensing, which involves observing the bending of light by large concentrations of matter in the universe, and baryon acoustic oscillations, which are sound waves that traveled through the early universe and left a subtle imprint on the distribution of galaxies. Despite the many challenges that still lie ahead, the study of dark energy is an exciting and an important area of research. It reminds us of the vastness and the complexity of the universe and the many mysteries that still await discovery. As we continue to unravel the mysteries of dark energy, we may one day be able to unlock new insights into the workings of the universe and our place within it. To truly appreciate the numbers and the scale and the complexity of dark energy, we must consider the sheer magnitude of the numbers involved. The universe is estimated to be about 14 billion years old, and the observable universe is about 93 billion light years in diameter. However, the actual size of the universe is likely much larger, as we can only really observe a small fraction of the entire cosmos because we are limited by the speed of light. We can't even begin to comprehend how much dark energy is out there in the cosmos, potentially waiting to rip the universe in half. To better understand the role of dark energy in the universe, we should consider its effects on the expansion of the cosmos. The rate of expansion of the universe is measured by the Hubble constant, which is the rate at which galaxies are moving away from each other. The current estimate for the Hubble's constant is about 73.3 kilometers per second per megaparsec, which means that for every megaparsec, which is about 3.26 million light years of distance between two galaxies, the relative velocity is increasing by 73.3 kilometers per second. However, this rate of expansion isn't constant. In fact, the expansion rate of the universe has been increasing over time, driven by the accelerating force of dark energy. This acceleration is measured by the parameter omega, which describes the pressure of dark energy relative to its energy density. If omega is less than -1, then dark energy is said to have phantom energy, which would cause the universe to eventually rip apart. If omega is greater than -1, then dark energy is said to have a cosmological constant, which would cause the universe to expand forever. Currently, the most precise estimate for omega that we have is about -1.04, which means that dark energy is causing the universe to accelerate, but not so much that it will tear it apart. This estimate is based on a combination of data from the CMB, Type 1a supernovae, and other similar observations. So what's next for the study of dark energy? Scientists are continuing to gather more data and develop new methods for studying this mysterious force. For example, the upcoming Wide Field Infrared Survey telescope WFIRST will be able to observe thousands of Type 1a supernovae and map the large-scale structure of the universe with unprecedented precision. This survey is a little far in the future. It's going to start in 2026, but the data that this survey will provide, combined with other observations, will allow scientists to really refine their estimates of properties of dark energy and hopefully gain new insights into its nature and behavior. In addition, scientists are exploring new theoretical models of dark energy, including modified gravity theories and theories that propose a new force altogether that interacts with dark matter. These models are still very speculative, but they offer new avenues for understanding the nature of dark energy and its role in the universe. So there you have it, the story of dark energy, the mysterious force that dominates the universe and propels galaxies away from each other at ever-increasing speeds. We know less about it than we do dark matter, and despite its enigmatic nature, scientists have made important strides in understanding it, from the discovery of its accelerating effect on the universe to the measurement of its properties through a variety of different observational methods. Although much about dark energy remains a mystery, the work of scientists like Perlmutter, Schmidt, and Reese, among many others, have given us important insights into the working of the universe. With new technologies and new discoveries on the horizon in the future, we may one day be able to solve the mystery of dark energy and unlock the secrets of the universe. Thank you for watching the video, and if you enjoyed it, please feel free to give it a quick like, subscribe, and hit the notification bell icon if you want to stay tuned for more content. This has been your host Yash Verma from WFIRST. Thank you for watching.